Okay, we are on to our final question of the paper. So we have some parametric equations. We have a restriction on t. The first part is show that this satisfies this. So you can see only y and x in here, so this is a Cartesian equation. We've got trig pieces, so what we're doing is we're looking for some strategy to try like an identity that features both of these things here. So the main thing I'm going to base it off is cos 2t. So we know that cos 2a is identical to, well, what's the version that's got sine in it? That's the one that's going to be most useful to me. So it's going to be cos, sine, sine. So it's going to be that one there. In fact, I should say that that's with a, but you see that it all kind of works anyway. So I think we might just jump straight into calling those t. So let's now put this result in here. So let's say that y is equal to, the 5 is just a 5 plus a 6. Let's put brackets for this one here. And we said it's 1 minus 2 sine squared. So 1 minus 2 sine squared t. Now, that is starting to look a little bit like that one there, but it still has t in it. So while we're here as well, let's rearrange this equation. So if we said x minus 2, that gives me 3 sine t. So how about we divide it by 3 while we're here as well? Okay, so x minus 2 over 3 is equal to sine t. That's not bad, but what would be even better is if we squared it, that's equal to sine squared, and now that could go over here, couldn't it? So should we do that? So that's going to be y equals 5 plus 6, 1 minus, going to be slightly careful here. So that's why I'm doing lots of bracketing. So sine squared is going to be x minus 2 over 3 all squared. So if we do a bit of tidying up, we should get to this result here underneath. So let's do a little bit of tidying up, because I think this is a show that question, isn't it? Yes, it is a show that question. So, well, that's going to be an easy fix. That's where our 11 is going to come from. This here it's got a bit more going on. So let's call this is equal to y equals 11. There's going to be still a 6 times a minus 2. So shall we say something like minus 12? Yeah, let's do minus 12. And I think we just, for the first, but I think we just write it out. It's not the worst idea in the world. Am I happy with that? Yeah, I'm happy with that. Okay, so next we need to remember that the indices are going to come first before the 12. So let's do y equals 11 minus 12. You know, we could have done this in the previous step, okay, but we don't really need to rush it. So it's equivalent to this sort of result here, okay? And the 3 squared is actually a 9. So that's where this bit's going to come from. So y equals 11 minus, you could write 12 over 9, and then you could write the result, I suppose. 11 minus 4 over 3, x minus 2 squared. I'm writing that extra y at the end because it's to show that result. So there we go. Sketch the curve. So sketching the curve is not going to be necessarily the easiest thing here. This is not too bad to sketch because you know some things about this curve. If you rewrite it as minus 4 over 3 x minus 2 squared plus 11, you'll hopefully see that it goes through the y-intercept at 11. It's a negative quadratic of some kind. So it's negative quadratic, and its turning point is going to be at 2. So, oh, sorry, I think I said 11 is the turning point. That's not necessarily the case. Its turning point would be at 11. So roughly, you know, it will do sort of something like this. The problem, however, is I've got a restriction here. So it's not necessarily going to be the case that I'm going to be able to draw the whole thing. If I look at 0 and 2 pi, and I think about my situation here is that I've got trig, right? So the graphs for sine and cos, if that's the first sort of 360 or 2 pi, cos, I'm not going to draw cos 2t, I'm just going to draw cos, would be like that. So cos 2t just makes this thing go even more quickly. But what this is doing to us is it's saying that sine and cos can get any of the values that they need. Well, that's fine, but they can only ever go between 1 and -1, can't they? So if you do these one at a time, like imagine for x, first of all, yeah? So for x, what's the smallest value that you could ever get for x? It would be when you did 2 minus 3, because sine being -1, 3 times -1 is -3, so 2 minus 3 is -1. So you cannot have any values to the left of -1. How about x's maximum value, for example? So that can only be 2 plus 3. So it would only ever go to 5. So it tells you that the whole graph has to be between, if you think about this left and right, it has to be between -1 sort of, you know, on the left and 5 on the right. And we can do the same for y. So we can think about the y minimum values and we can think about the y maximum values. So 5 and there's a 6. So I'm just going to read this as 5 plus 6 and 5 minus 6. That's how I read this one here. So the minimum y value would be a -1 that we could get to. And the maximum there would be an 11. And 11 just came up a minute ago, actually, didn't it, in our discussion? So it's going to be like a negative quadratic, but it can only take place, you know, if I kind of get rid of that, it can only take place, in fact, let's do it with the eraser. It can only take place, really, between -1 and, let's say, 5. So I don't know exactly where these points are yet. I'm just sort of, you know, talking about the idea of domain and range, really. That's what we're doing. Y going down to -1 and going up to 11. So we've come up with a box that the quadratic is going to be in. So it's part of a quadratic that exists just in this box. I could use now like a graphing calculator just to kind of help me come up with it. But quite a good way to do it would be to put this in your calculator from -1 to 0 to 1 to 2. What are we going up to? Because there's not that many values, this is probably not the worst way to do it, I'm thinking, just time-wise. Okay, so I'd put these values in, and I'm just going to do that myself to see what that looks like. So 11 minus 4 over 3, x minus 2 squared. Yeah, it looks pretty much like what we said, really. So if I draw it a little bit more accurately for you, because I'm sure you're interested to know at this point here what it looks like. So if I expand out all the numbers, I can get the y-intercept. The y-intercept is not a nice number, so it's 5 2/3. At 211, there's a turning point. And then what I would do is I would just check for the roots, and the roots are actually in between that. So this root here is, again, is not a nice number, so it's -0.8723. And is there a root less than 5? Yes, there is. So this is just less than 5. It's 4.8723. So you get a graph that goes a tiny bit to the right, a tiny bit to the left of there, but essentially does something like this, okay? And looking at the x min and max and y min and max tells you that this whole thing just takes place inside sort of a little box. So, explain briefly why C does not include every point. I think we've just discussed that, no? So, you want to just talk about there's a restriction. Because of the restriction in T, the domain and range is limited, and I've even given the values there. So, that's definitely going to be enough for that when we write all of that down. Now, finally,